It is late in the day, so these slides are a bit dry. So I will try to keep things interesting. So most of you know me from I assume from the Pandas project, which was what is it today? It's April 10th. So it was around this week, 10 years ago, that I started writing a few lines of code just to solve a few really annoying data problems that I had right in front of me. And you know how it goes: you start pulling on one thread, and the whole sweater comes undone. So that code base turned into the Pandas project, which became an open source project at the beginning of 2010, and I built out the project and maintained it actively until around mid 2013, and then handed off the project to a group of core maintainers, some of whom are here at AnacondaCon, but folks like Jeff Reback, Philip Cloud, Joris van den Bosch, Tom Augsburger, people that if you've contributed to the Pandas project in the last 5 years, you will have run into these people. So if you do see them online or in the real world, please do thank them, for the work that they've done, maintaining the project and making it, into the thing that it is today. I've done a bunch of projects since 2012. While I was working on Pandas, I wrote my book in part to encourage myself to finish parts of Pandas so that I could write chapters about them. So you get to this blank section, you'd be like, well, I really want to write about this thing that doesn't exist yet. So I would write the code, and then I would write the section of the chapter. I was a startup founder for a little while. I had a little company called Datapad. We later joined Cloudera at the end of 2014. And that's when I got to sort of dive into the big data world. Projects happening in the Apache Software Foundation, the Spark community, the Hadoop community. And one of the things that impressed on me immediately, I had accumulated by then a list of complaints and grievances about things that made Pandas really hard to build and things that were causing Pandas users a lot of pain on a day-to-day basis. And to my surprise, I found that many of the problems that I'd encountered working on Pandas were not, maybe not surprisingly, were not distinct to Python or not distinct to Pandas, but they were the kinds of problems that are experienced all around the world of data processing. And so for me, one of the best parts of being at Cloudera and being in the center of the Hadoop ecosystem, the big data world, was that I was able to start and build relationships with a lot of different open source projects. And so I started for the first time to look outside the Python community how we could build have more healthy collaborations with other programming languages and other data system developers to make the whole ecosystem stronger and more successful, and preferably make things better for Python programmers as well. So one of the major artifacts that came out of initially, I helped start while I was at Cloudera, is this project called Apache Arrow. And so if you it's an interesting project, and I'm going to tell you all about it over the next 44 minutes. But it can be a little bit inscrutable to outsiders. Like, we were just outside joking about how, everyone's here saying, like, oh, Wes is here giving a talk, and the Arrow project is sort of, somebody called it inside baseball, where if you're building data systems, it's really interesting because you're like, oh, this solves this problem that I had, or these set of problems that I've had. So I started, prototyping some low-level systems for sharing data between different systems. So one of the problems I was looking at was adding more efficient user-defined functions to Spark and to Impala, which is a distributed SQL engine. And so immediately I was like, well, how do I make data available from this SQL engine to Python so that I can run Pandas code on it? And so I had to kind of define this define some kind of efficient way to exchange data between two systems. And I dug around, and I was like, there's not something that I can pick up off the shelf that's a really good solution to this problem. So I started thinking about like what would a good solution to this look like, and sort of went around Cloudera and found there were other people inside Cloudera that had been thinking about this problem. Pretty quick, soon we branched out. We encountered some other open source projects. There was a bunch of folks from the Apache Drill project, which is another SQL engine. We joined forces with them, and it took, most of 2015 we spent basically just talking to people and figuring out like who's experienced challenges sharing data between systems and reusing algorithms on data. And it turned out there's a lot of people that had that problem. We got as many of those people as we could in the room, and we decided to work together to create an open source project to build some technology that would make all of our lives as system developers easier. So that got going at the end of 2015. It took us a few months to set up the governance structure for the project so that we made sure that we were building a community-focused, community-led project that wasn't being driven by a single vendor. So as with any open source projects, whenever you have big corporations involved, it can get very sensitive because there's concern about whether maybe that project is part of some kind of a product development agenda. So we were very careful. We had a lot of, we even had a bunch of companies involved in Arrow at the get-go, which are in direct competition in the market. And so we wanted to make sure that everyone could collaborate without fear of some kind of product agenda or some kind of financial incentive to drive an open source initiative. That's part of why we did it in the Apache Software Foundation, was to head off that concern from the get-go. So some of the problems that we'd encountered, and you'll forgive me for the dryness of all of this, but so when you build a data processing engine, so if you consider pandas, so when I started building pandas, I was faced with all of these decisions that I had to make. So decisions like how do we represent missing data? How do we represent strings? How does mutation work? Like kind of all of these really basic things that you have to make a decision. The decision might be arbitrary, but you have to have some decision that you make and then be consistent about it. And then you're kind of stuck with those decisions for forever. So really basic things in pandas, like the fact that we represent strings as NumPy arrays of Python objects, and that we support either not a number or none as a null value in those arrays for missing data. Like that was something that was decided in the project very early on. And so anytime you build any kind of a data processing system, you have to make all of these decisions. And those, the sum of all of those decisions is what I would describe as the memory format for all of your computations. Because if you're going to write an algorithm which says, okay, I'm going to apply some computations to this data frame or to this array, the algorithm needs to know about those low-level details about how you've represented missing data, how you're representing strings, kind of all of that stuff. And so if the memory format changes, the algorithms have to change, and vice versa. So it would be really beneficial if there was a suitable standardized memory format that could be used off the shelf for building query engines, in particular high-performance analytical query engines. Another big use case is the data interchange use case, where you have two different systems which need to be able to move large amounts of data between one process's memory space and another. And preferably, you would like to say, hey, here's this data set. I'm going to give this data set to you. Here's the column names, the column types. Here's how big it is, and here's where to find it. And that turns out to be a really complicated problem, particularly when you have complex data sets. Like you might have a column which contains structs, or you might have a column which contains variable length lists of integers. So the structure of the data set could be very complex. And so when you get down into the details of communicating what that data set is to the other process, there's this list of maybe like 50 or 100 decisions you have to make for two systems to be able to agree on what that data is. Preferably, you would also like to be able to expose data from one process to another without having to go through expensive serialization. So sometimes what happens when you use, like if you know, one of the crudest serialization forms would be CSV or JSON. And in fact, you know, in a lot of cases, that's how systems interchange data. So you're using Python, you're using R, you know, be like, well, we don't have a common format, so we're just going to dump the data to a CSV file and then read it in the other process, and that's very wasteful. So it would be great if, no matter how complex the data set is, you could give that data set to another process at zero cost. Very closely related to that, that data interchange or data handoff problem is the problem of sending data through streaming services, through sockets, through any kind of messaging layers. So if you look at, you know, if you profile systems that move data around over the network, they spend a lot of time taking data that's in memory and converting it to some representation that they can send over a socket or send over some kind of wire, you know, whether it's like a socket or 0MQ or, you know, WebSockets, one of these things. And on the receiver side, the receiver must take that data and convert it to whatever in-memory representation they use. So if this were, you know, so whenever you're using Jupyter, the messaging layer that's being used is JSON for the most part, and the data is being sent through 0MQ or through WebSockets or both, depending on, you know, what kernel you're using and kind of a number of details. Another problem is building file formats and ways to store data is very complicated for all of the same reasons that these other problems are complicated. So I'll talk about that. Another problem is the fact that for any given data format, developers have to write data access layers to read that data. So as an example, Pandas has its own CSV reader, and it's funny when you go back in time, because once upon a time it was really difficult to read CSV files in Python. And it might seem crazy now, because now, like, you know, you open IPython, you write import pandas, pandas read CSV. This is something that we take for granted, but, you know, this used to be really hard. And there was a point in time, I think it was maybe 7 years ago, where a lot of us got together here in Austin, and we were like, we need to fix the CSV problem. Like, we need to just be able to read CSV files. Like, if we can solve that problem, we could move on to bigger problems. But when you think about, you know, it's not just Pandas had to build its own CSV reader or its own JSON reader or its own interface to, you know, there's many other, you know, file formats and protocols for accessing data. And people use Pandas. One of the reasons that Pandas has gotten so popular is that it's one of the primary kind of ingress points for data into Python. It's like data comes from CSV files, data comes from SQL. You know, a lot of people use Pandas just to get access to data. But any given system, whether it might be not just in Python, it might be in R, it might be in Julia, like everyone's having to write their own data access layers. They're writing their own CSV converters. So there's a lot of redundant work that is happening, particularly when you consider the whole world of data science and data engineering, and not just limited to the scope of the Python ecosystem. So if we could make it so that people building data processing systems didn't have to spend so much time writing data access layers, writing CSV parsers, that would be great, because we could move on and we could work on, you know, other things that are of high value to the data science world. So just to kind of, that's a lot of information. So I'll try to, you know, recap some of the big pictures here. So one of the primary kind of initial purposes of building the Arrow project was to deal with this n-choose-2 kind of combinatorial data interchange problem, where system A has data, system B wants that data. If we had a standardized way to exchange, and it might be that two systems have some super optimized way to interchange data, but at least we have some standardized way that everyone can, hopefully as many of these parties can agree on to implement. And so if two systems speak Arrow, then they don't, you know, necessarily have to build a custom converter. They would say, okay, I speak Arrow, you speak Arrow, here's some Arrow data. So when we started the project, the primary focus of the Apache Arrow project was designing a column-oriented memory format effectively for data frames. So if you look at Pandas, Pandas has its own columnar memory format, which is layered on top of NumPy. So essentially, we have NumPy arrays inside the Pandas data frame with a bunch of assumptions, things like, here's how we represent missing data. Here's how we don't represent missing data in integer arrays, things like that. We wanted this format to be suitable as a memory representation for query processing. So if you load data into Arrow format, that's a perfectly reasonable way to have the data in RAM for running algorithms on it for doing analytics. So we wouldn't want to have to convert it to some other kind of more specialized memory format for doing the kind of stuff that you do with Pandas. We wanted it to be not a replacement for, so when people see the word columnar, one of the major associations with the word columnar is columnar storage. So things like Parquet format, ORC format is another column-oriented storage format in the Hadoop ecosystem. So it's not a replacement for storage formats. It's a companion technology where you would put data that comes out of those storage formats when it's loaded into memory. So if you're a database geek, the style of columnar that we're using is what's called fully shredded columnar, which means that when you have nested data, so let's say that you have like a struct, or like what in Python would be a list of dictionaries. The inner data in those dictionaries all of it is contiguous in the leaves. So if I have like a list of dictionaries, each key in those dictionaries, the data for that key is stored in a separate array. I really should have a graphic for that, so I'll add a graphic for the next slide deck. But the reason for the way that we designed the format was to make accessing the memory very efficient on modern hardware. So if you put the data on a modern CPU, which has SIMD instructions, very good at processing arrays of data, we would want that to be as efficient as possible for the CPU cache. We want it to work well on GPUs, and so we're already seeing Arrow used on GPUs. I'll say a few words about that. We also wanted it to support both very cheap random access, so you can get single values in constant time out of an Arrow data frame or table, whatever you want to call it. But that also it's efficient for scanning. So databases typically scan tables, like they don't do random access. Where people that use Pandas, sometimes they scan, sometimes they do random access. So the format needs to support those things equally well. The project has expanded to not just be about column-oriented data and memory formats. So that was the thing that we focused on 2 years ago at the start of the project. But over time, we've been acquiring more components that are related to the general problem of sharing data and data interoperability. So one of the pieces that the project inherited was called Plasma. It is what's called an object store that manages shared memory blocks between processes. So it was developed as part of the Ray project at the RISE lab at UC Berkeley. And so the original idea of Plasma is that if you have two Python processes that need to access the same large data set, you would like to be able to keep track of how many processes have a reference to a particular data set, to be able to hand off, say, hey, I'm going to run this function on this NumPy array, and then as soon as you're done with that NumPy array, you tell Plasma, like, okay, I'm done, and Plasma will decref the reference count for that memory. And then if there's another process that still has a reference to that NumPy array, which could be a different Python process, the data won't get deleted, but as soon as everyone is done with that data, it gets garbage collected. And so it's essentially enabling distributed computing on large data sets without having to move data around. You can just operate on the data operate on the data in place. So if you check out the Ray project, which is being used for reinforcement learning and deep learning, it's using Plasma under the hood to manage data on the nodes. We've been growing a lot of different implementations and bindings for the different Arrow libraries. I need to now expand this diagram because we have now a few very active Rust developers building a native Rust language implementation. So we started out, to just give you an idea, the first code that was into the project was extracted from the Apache Drill project, which is a SQL engine. So the initial Java implementation was initially a component of a SQL database. The C++ implementation was started from scratch in the project. And since then, we've acquired a JavaScript code base, which was started from scratch. A company called Influx Data, which develops InfluxDB, built a Go implementation, native Go implementation that uses unsafe memory. That was just donated to the project. Rust is in progress. Some folks are starting to look at R bindings. When you see Python-related Arrow code, we're building bindings to the C++ library, but there's also, there's so many layers here, it's kind of like Inception, but there's Ruby developers in Japan that are building Arrow bindings, but they are going through C to C++. So there's two layers of bindings there. And through the C library, through some magic, which I don't completely understand, you can generate bindings in many other languages, which is pretty neat. So we've been lucky to acquire quite a lot of major contributors from different players you may recognize in the industry. I work at 2 Sigma in New York, and so myself and a bunch of my colleagues there. One of the reasons that I moved from Cloudera to 2 Sigma was to get sort of more support and budget for working on Arrow. We've been collaborating with Databricks on Spark integration of Arrow. So if you check out Arrow and Spark, you can see some of the work that's happened there on speeding up Python on Spark. Folks at CCRI and Graphistry have been working together on the JavaScript implementation. Dremio has been leading the Java implementation. So the folks that I worked with initially on getting the project off the ground. But we're very actively recruiting more companies that use Arrow or have an interest in the problems that Arrow solves to get involved in the project. It's been we're sort of at an inflection point. This is not the best graph, but you can sort of see that the project started in early 2016. That at some point in 2017 we hit an inflection point, and the project has been growing very fast. And the growth rate has been continuing as we're getting more and more people involved. So we have over 130 contributors to the project now. It's hard to measure how many installs we have, but our best estimate is that somewhere around 100,000 installs per month on the various install paths. Like I think just on CondaForge on Anaconda.org, there's over 1,000 downloads of the libraries per day. So it's been exciting to kind of have this brand new open source project and get it to a point of not quite exponential growth, but things are growing very fast, and I think that trend will continue as more and more people adopt the project for their, as a library inside other projects that they're building. So we just made the 9th major release of the libraries two weeks ago. What is it? It's been 3 weeks, almost 3 weeks. So to this point, building a project like this is very, I guess it may be hard from the outside if you aren't working actively in the project to see all of the details that go into building something like this. But just hardening the details and stabilizing the fine details of the memory format and how we're dealing with messaging, things like schemas and the particular details of how the data is laid out in a stream. That's taken up most of our energy over the last couple of years, and making sure that the different language implementations are doing exactly the same thing. Because what we don't want to do is to have Python thinks the data looks like this, JavaScript receives the data and decides that it's something else, and then you compute things on both sides and you get different answers. So anything related to correctness and binary formats, you must be extremely careful, because producing, in my opinion, producing incorrect answers in a data library is not acceptable. So, you've got to get this stuff right from the very beginning. We've spent a lot of time on data access. So it's it would not be much use to have a memory layer without the ability to get data into it. So one of the first proof points was building out kind of low-level integration with columnar file formats. So I've worked a lot on the Parquet integration. We've been collaborating with Anaconda on the ORC file integration. So having good affinity for working with columnar storage formats is really important to kind of prove that the project does what it claims to do. We've been collaborating with downstream projects like Pandas and making sure we have really good ability to convert between Arrow format and Pandas format. And we've been working with the Spark project as a first kind of using Arrow to accelerate existing code. So if you use Python on Spark, there is now a Pandas UDF sort of mode that you can use to run, rather than running passing Spark a Lambda function that processes one value at a time or one row at a time of a data frame. You can write functions which expect to receive Pandas data frames or Pandas series, and Spark will pass whole blocks of data through using the Arrow format as the intermediary, and those will enter the Python world as Pandas data frames. And so we've seen 50x or 100x speed up by plugging in that technology there. So that's been really exciting. So if you're interested in keeping track of what projects are using Arrow, on the Arrow website we have from the front page there's a powered by page where we keep track of all the different projects that are using Arrow in some form. So we've been collaborating with the Dask developers on data access. There's some folks in I think they're in the Netherlands, and they're building a middleware framework for using Arrow on FPGAs, which is really interesting. I don't know much about FPGAs, but this might be an interesting way to learn more about FPGAs. There's a bunch of GPU-related projects. I'm about to say a few words about those. There's some folks at JP Morgan which started this project called Perspective, which is a streaming data visualization engine in JavaScript, and they're using Arrow for data interchange to the browser. The JavaScript library is really cool. I haven't dug too much into it, but the whole idea that I can in JavaScript pass a URL which contains binary data in Arrow format, and that can be loaded into the browser in JavaScript. And let me try to find some. So here's some code in JavaScript where we have, basically an Arrow JavaScript data frame, and they're developing Pandas-like APIs in JavaScript which are interacting directly on binary data set client side in the browser. So there's no intermediate conversion to JSON or any of the kind of usual JavaScript tools. It's all direct binary typed arrays in JavaScript. So very cool. if I know how to use Google. Okay. So one cool thing that's that's happened as the result of industry collaborations is initially all of us who started the Arrow project were concerned with CPU side data processing, and so kind of completely unrelated to our kind of day-to-day work. NVIDIA and MapD and Anaconda, H2O, Graphistry, and a bunch of folks who all have an interest in doing analytics directly on graphics cards. We're exploring the idea of building some interoperability technology and shared tools for processing data frame-like data on graphics cards. So they decided they initially experimented with using Arrow as the data format on the GPU, and they found that it worked. Pretty well. So they decided to work together to define what is a GPU data frame, and that's implemented as putting Arrow memory on the GPU. And so since then, within the Arrow project, we've done a couple of pieces of work to help with folks who are using CUDA. So we extended the plasma store to be able to manage shared memory on GPUs. Like CUDA provides a way to share memory regions between processes. We started an extension library for dealing with kind of the C++ memory model, like object model, and the fine details of dealing with memory that's managed by the CUDA runtime. So there's some low-level details that are made much simpler by this extension library. And one thing that I'm really excited about over the next couple of years is building computational tools which can, basically with the flip of a switch, you can run algorithms either on the CPU or GPU, depending on where the data is. So, I foresee kind of in the future being able to transparently do analytics kind of wherever the data is without having to rewrite or do significant rewrites to your code. So that if you do have data on the GPU, you can take advantage of the GPU acceleration without a great deal of hardship for you as the developer. So I'm going to say a few words about some directions where the project is going over the next 1 to 2 years. So if you are a systems developer and would like to get involved in any of these problems, or you have folks that you work with who might like to work on a systems project, these are some areas where we certainly could use the help. The project has grown quite large, and it's far too much for an individual like myself to do all on his or her own. So there's plenty of ways that folks could be useful to the project. So one area is we've so far been spending a lot of time on dealing with columnar storage formats, but there's many other ways that data is stored and archived. And we'd like to have first-class native Arrow-based implementations of readers and writers for all of these formats that get used. And so the idea is that if you have a system which uses Arrow and you encounter a particular data format, it would be nice to have, for any given data format, an off-the-shelf component that you can pick up to natively read and write that data format without having to go through some other intermediary. These all can be community maintained, and over time, the quality of these data access or data export, import and export layers will, preferably we'll have one really good implementation of these things, rather than dozens of implementations that all have different features and performance characteristics. Building a complex open source project is not without its share of software development lifecycle headaches. So now that we're a little over 2 years into the project, we're at a point where We need to do a lot of work on continuous software delivery. It's not the most exciting thing to talk about in a conference talk, but in terms of like things that impact my quality of life on like a week-to-week or month-to-month basis, like building packages so that whenever we decide to tag a release, that we can ship all of the Python packages on all of the different installation targets, because we don't just have to do Conda, we also have to build wheels for Python 3.5, 3.6, 2.7, but not Windows in 2.7 on all three platforms. So it's just for Python, there's a lot of packaging work, but now that we're accumulating more programming languages and our matrix of supported components is growing larger, so the complexity of the software development lifecycle is getting a lot more complicated as well. We don't have build farms that can do GPU-enabled builds. So, when we want to get more serious about delivering more, CUDA or OpenCL-based Arrow libraries, we're going to need to be able to do continuous delivery for those packages as well. And there's other kinds of like software quality and testing things that we need to do. So if you have release engineers in your company, or you find that you're passionate for the operational side of software development, so maybe less doing Arrow feature work, but more like the process of building the project itself, would love to have you involved in this. Some people really like this stuff. Like I personally do not, but it's work that must get done. For me, probably the most exciting thing that I'll be working on over the next couple of years is building computational libraries which operate natively on the Arrow memory format. So far, we've been concerned with low-level details of like, how do I send data from Python to JavaScript or from Java to C++? So far, I mean, that's going well, and we have that, 90% complete. There's some fine details that we're still working out. But with that all stabilized, we can begin to move on to building computation engines which process the Arrow memory. So the way I see this layering is building a library of reusable, what I call kernel functions. So if you think of, I guess I call them kernels after stuff like the Intel math kernel library. So primitive analytic functions for doing the kinds of things that you would use to build libraries like pandas. So basic array manipulations, analytics that involve missing data. You'd like to have good canonical implementations of all of those kinds of things that you do, string processing, and so forth. For as many of these as possible, it would be great to have both CPU and GPU flavored variants, preferably that you can switch which, depending if the data is on the GPU or the data is on CPU RAM, you can just select the kernel that you want for the given type of data that you're working with. Similar to deep learning systems like TensorFlow, we'll need to be able to create high-level operator graphs to compose kernel functions to describe computation that is yet to be evaluated. So this would be the equivalent of like lazy pandas, or things that Dask is already doing. So these operator graphs would be, so if you look at the Dremio platform, that is already a Arrow native computation engine, which is written in Java, that has basically all of these things. They're even working on some LLVM stuff, I believe. I'm very interested in building code generation infrastructure using LLVM that can generate Arrow native function kernels. So we can take operators and generate specialized versions of groups of operators that evaluate more efficiently, given kind of the fact that if we can exploit our knowledge of the operator graph to generate more efficient versions of things. And then finally, we need to be able to take all of this stuff and actually, if you think about the code that you write when you're using pandas, the runtime engine is the internal system which takes the code that you write in Python, executes it, and returns the answer to you. So I would like to have portable libraries which are not coupled to Python that could be used in any programming language that can evaluate generic operator graphs. So kind of the way I think about, and I'm running low on time, so I'll try not to bore you too much with this, but kind of my high-level kind of way I look at the ecosystem from having worked on this stuff for a long time is, if you think about how NumPy and a lot of the Python world was architected in the mid to late 90s when all this stuff got started. In a way, NumPy and equivalent stuff in R and MATLAB, other programming languages, was an interpreted version of what scientists were already doing in Fortran. And so it was incredibly useful to be able to write interpreted code and do the exact same things that you're doing in Fortran, but there's definitely parts of the ecosystem that have not evolved very quickly. We're still doing a lot of very single-threaded things. Our memory management is not very sophisticated. One of the problems that Arrow is trying to solve is the fragmentation problem across programming languages, that everyone has a different memory model. So that means that it's basically impossible to, if I write an algorithm for use with Pandas data frames, an R person cannot take my algorithm and run it on R data frames. They have to rewrite the code. So I see that as like kind of a design issue. It would be nice to be able to collaborate with the R community or collaborate with the Julia or the MATLAB community to share algorithms for processing data frames. A lot of Pandas users are struggling to work with medium-sized data, so that's data in the tens to the hundreds of gigabytes. So systems like Dask data frame have been mitigating this problem significantly, but I think there's still work that we can do to make at the single process level to make things a great deal more efficient for working with large data sets that fall into this medium data category. So if you look at all my talks from the last 5 years, I guess I've been sort of obsessed with this medium data problem for a long time. So my feeling is that we can do a lot better on a lot of these problems, with building multi-core versions of a lot of our algorithms, using code generation, which there's already plenty of code generation tools you can pick up now, like Numba, and Julia is a whole programming language built around code generation. Using GPUs for more of our analytics, I think, given that this whole Moore's law thing, which is kind of stalling out right now, so going multi-core and GPU as the next the next frontier of performance and scalability, I think is where a lot of work is going to need to be invested. So this is all a pretty ambitious roadmap, but where I'm going to be spending my time over the next several years is I'm really excited about building next generation data science systems, which are powered by Arrow, and I've spent the last few years essentially laying the foundation for this work. My hope is for the libraries that are produced by this effort to be usable across programming languages, so not just from Python, that we can see have libraries which are consumed by the R community, or we can have code that is written by folks in the R community that we use in the Python world. And so when we started the Arrow project, I sat down with Hadley Wickham from the R community. We created the Feather file format, and the idea there was we wanted to socialize the idea of what if we had a lot more libraries like this, where we had libraries where there's very few examples where you have an R library and a Python library where they actually are sharing a non-trivial amount of C or C++ code. So I think we were both excited about the possibilities there, and I think we'll see more of that in the future as we begin to kind of deal with this chicken and egg problem of using interoperable memory technology. Another interesting thing is I think we'll see different front ends developed. So right now, you use Pandas. The Pandas front end, the code that you write in Python, is very coupled to particular details of how Pandas works internally and internal details of Pandas. So I think we'll be able to develop different styles of user interfaces for interacting with data frames. So You can build a different kind of data frame interface without having to throw away all of the computational algorithms and systems codes that things are built on top of. And that's often a thing that people come to me, they say, hey, Wes, like, you know, love pandas 80%. It's like that 20% of stuff that drives me crazy. And so if there was the freedom to be able to tweak the front end and to change and sort of more, you know, quickly make or develop different kinds of user interfaces for interacting with tabular data, I think that would be really useful. And all of this work will be, you know, my intent is for it to be, you know, built and created as a companion to, you know, distributed systems like Dask and Ray. And so, so when I've talked about this stuff, people say like, well, what about Dask? What about Ray? It's like, well, you know, there's a lot of work to be done at the single node, you know, single process, multi-core level, and that all that work is wholly complementary with the work on distributed systems that has already been happening the last few years in the Python data world. So, so completely complementary, and I'll be excited to see what those collaborations look like in the future. So that was a lot of information, but I will put these slides online, and if you know, you'd like to get involved or have questions, please join us on the mailing list, or you know, come to a conference and we can talk some more. But I think the next few years are going to be really exciting. I would say when I started this out, there was maybe the first year or so, I'm like, is this all going to work out? And now that we've reached the inflection point and the community is growing, like you know, we're on a good path, and I think it's going to produce a lot of really valuable software for the Python community over the next 3 to 5 years. So, thank you.